I'm not so much going to save the planet, which is a totally laudable thing that we should all pay attention to, nor am I necessarily going to tell you how to do your day job better. This one is a little bit more for a bit of fun. So, oh, is that getting in the way? Yeah, is that better? There. So I'm going to talk about steganography. Steganography is in the same sphere as things like cryptography, but the emphasis is a bit different. With cryptography, you're potentially passing the text around in the open, but it's re-rendered in a form that's illegible. Steganography involves hiding the message so that no one even knows it's there in the first place. Now, steganography's got a long and quite interesting history. This is the Greek historian, which looks like it's Herodotus. I think there's all sorts of ways of saying that in English, but according to the text down there, there's his name. So there we go. He wrote histories about wars in ancient Greece, and he described the first two classical examples we know of steganography. The first being writing back then was done on a wooden board with wax on the front, and then you would write on the wax tablet and pass that around. People would, to conceal messages, write them direct onto the wood underneath the wax, put the wax on top with a boring message, and then someone would know to scrape the wax off and look at the real message. But the really funny one, which I don't know how many of you have heard of this, but this is one I absolutely adore, was a story about a military leader called Hystaios, I think is how you say that. He's not here to check up on me, but he wanted to send a message to some Greek folks in cities that were under enemy control. So what he did was he got himself a slave. He cut the guy's hair off, tattooed the message onto the guy's skull, let the hair regrow, and then sent him on his way to through the enemy lines, where people would just have to send him to a decent hairdressers to find out what the secret message was. I'm not saying that's necessarily a true story, but that's what he said happened. So I don't know. Still, I think that's pretty cool. I wish I could think of some sort of hair-related pun at this point, but I can't. But there we go. It's been going on an awfully long time. This rather awesome lady comes from World War II. She is Simone Seguin. I think is how you say that. She was a member of the French resistance. She's just here to point out that there were all sorts of ways of hiding secret messages during World War II. They would do things like playing a particular piece of music on the World Service was a sign that something should happen. Or sometimes they would read out a series of absolute nonsense texts, like mostly random quotes from different books. But someone would know that when a particular quote was read, that was the sign to proceed and blow up the enemies or whatever it is you wanted to do. So again, it's something that we're still doing kind of to this day. This is a microdot. We might have seen these in old spy films. I think this particular one comes from a Mission Impossible film, though I have only seen the first two of those. But you get the idea. It's the same idea. The message is hidden there on the back of the stamp, teeny tiny, unless you know the secret way to read it. I guess a really big magnifying glass. So I want to find a way to do some code that will let us do some steganography. I want to hide a message inside an image. Inside, in fact, it's going to be using PNG. I don't think you could do this with some of the more compressed, forms, but certainly PNG works treat. So I need a test image to work this on. There's a tradition amongst folks that do image processing to use this image. I don't know if anyone has already seen this before. This is Lena Sjöblom. She was a model, and she worked, amongst other things, with Kodak to produce images. Now, for some reason, now goodness alone knows why, a chap called Dr. William K. Pratt at the University of South California, who was working on a new image compression technique, which eventually became known as JPEG, decided to scan a copy of a Playboy magazine, which is what this is from. He actually chose it amongst other reasons because of the nice mix of textures and colors and so on and so forth. But yeah, if I'm not going to, but if I could magically extend out the image, the hat is actually all she's wearing. So I'm not sure this is really entirely appropriate. That's a discussion maybe for another day. So instead, that bit of interesting history aside, I'm going to use a picture of my favourite sweet when I was a kid. Desperate Dan bars. I don't know if there's a chat open or anything, but anyone remember Desperate Dan bars? They were fantastic. They were like, for all the kids in the audience, they were orange chews with black sugar crystals inside them. They were brilliant. Also, Desperate Dan, for the kids in the audience, is a comic character. Yeah, I'm probably showing my age in all sorts of ways now. But anyway, Desperate Dan, he's awesome. And I'm going to hide the text of Pride and Prejudice inside it, or as much as I can of it, because it's a really, really good book. And because, I've used it recently, so I had it to hand. So let's consider the opening of Pride and Prejudice, which actually, in the text file I used, is literally the words of the title. There we go. I'm using underscores here to represent spaces, so don't get hung up on the underscores. Otherwise it wouldn't show up. But anyway, those are our letters. We're going to just look at how I would work through an example of how I'd encode these letters. These all, of course, re-render into ASCII. Is there actually a chat on this thing? I can't see it more. Chat. There is chat. Wonderful. There we go. Sorry. Apologies to anyone who I have not. Ooh, we have had a whole load of chats. Okay. Metal Mickey Fizz Bombs were the best. I have never heard of a Metal Mickey Fizz Bomb. That sounds kind of awesome. And Shatty Teeth of the Two. Oh, yeah. And Iron Brew Bars. Yes, I think you could still get those. Might be mistaken. Right. Pride and Prejudice. So in ASCII, I'm hoping everyone's good. Wham bars. You could definitely still get wham bars. They are still just as good. Okay. These are the ASCII characters for these letters. Great. And then those will re-render into binary like this. I'm hoping, again, given that this is a .NET group, that we're all good with binary. If you are not, it's going to be a tough 10 minutes. So binary, this is what this whole thing encodes into. Great stuff. So now let's have a look at the image. This is the first pixel. It's got a pixel, consists of 3 values. They're all integers. They're all between 0 and 255. They are, so in this case, it's red is 36, green is 139, and blue is 206. That is this pixel, I think, right at the top here. It's sort of lighty blue. Looking at the second one, it's roughly the same. Interesting thing to note, this appears to be one color, and yet it's very, very, very slightly different. 36 to 35 here, 139, 138 here, and so on. But honestly, human eye can't actually see the difference very much between these, at least not on the slightly inexpensive screen that I'm currently looking at them on. But the point is that we can actually tweak these colors very slightly, and no one's ever going to know, which is, where we're going to have our fun. So looking at the first 4 pixels then, this is them shown with color coding, just so you can tell, which is in binary looks like this. Bang in Pride and Prejudice. So the way we actually hide our image is to take the least significant bit, which is this one right here. This one's worth 1. So this one way over here is worth something like 128. This one down here is worth 1. So a difference of 1, who's ever going to see it? And that is where we start to insert our data. We're going to go through these pixels one at a time. We'll grab that one there, shove it there, that one there, shove it there, and so on. Looks like this now. So I've highlighted the last one in yellow just to show these are my replacements. But if you notice, actually, an awful lot of them were the same as what they were before. I've just highlighted in yellow those values that have actually changed. Not all that many of them compared.
Sure. I think, is there a wave?
I don't know what that was, but it scared me. Right. So, Texan bars. I don't think I've ever had a Texan bar, but fruit salads, you nearly had me at fruit salads, except my favorite were Apple Jacks. Apple Jacks were the best, and I will fight anyone that says otherwise. Only thing is, what happened is they found out I like them, so they stopped making them. That's what happens when they find out I like things. Right. Anyway, so this is what we do. We going through a bit at a time, replacing 1 bit out of each of these bytes, one at a time, in each of these values inside our pixels. And that's actually what it looks like. Don't look very different, of course, because it really isn't. To the human eye, the difference between the original picture and this one, totally impossible to tell. This is a 500 by 310 pixel image, which means it contains 155,000 pixels, which means I could fit in a 465,000 values, which is, roughly speaking, 56K. So I can fit 56K of text straight up just using that basic, simplest possible version of this technique. But we could do an awful lot better. Anyone want to take a guess at what percentage? Kevin Smith says there's a bitmap. Yeah, this is a PNG, which basically operates like a bitmap. I'll show you some code in a minute. So anyone want to take a guess at how much of the book fits inside this image now, just replacing 1 bit and 1 pixel? 50%? Oh, I wish. 22%. But let us bear in mind that Pride and Prejudice is quite a big book. It's something like 3 volumes long. I think the audio book is 1 second, hold on there. Yep, GZIP, I'm well ahead of you. Yeah, so how can we improve this? First off, this is what the text, I'm not going to dwell too much on this because times are limited, but there we go. This is kind of what we're doing. To play around with binary, we have to do a whole load of bit shifting and logical anding. I'm not really going to go much over this, but happy to talk about it to anyone that wants to have a copy. This is how you do your pixel inserts. It's just going by and using, again, logical or, logical and, stuff like this to, and a negation there to put in a 1 or a 0. So it's fairly trivial stuff if you've ever done a little bit of messing around with binary. But again, anyone wants to see this in more, fine, I will talk to you afterwards. That's how you read it. I'm using yield returns for anyone. I'm surprised how few people use about yield returns, but that's just a shorthand way of just saying this one, this one, this one, and then keep returning that one, stuck them all together in an enumerable in that order. Imagine there's a virtual list up the top here, and we're doing adds to it here. But anyway, that's how you'd read out of it, again, using a logical and. Yield return rocks, it does. It really does. So, returning to our binary, let's see how we can improve this. There is something, I don't know if anyone notices here, and that is the most significant bit is always 0. You can, and this is the ASCII table. The highest value in the basic ASCII table, the simple ASCII table, is 127, which I think is a 0 and about 7 ones on the end of it. There are ASCII values beyond this, but that's the extended ASCII table. So if you were having a text that was in German or French, you might need to. But as it happens, I'm using an English text. It's Pride and Prejudice. I happen to know there aren't any accents in it. So we can actually abandon one whole pixel. Which is literally just, let's just not do that one. Let's just ignore it. Let's just assume it's 0. So anyone want to take a guess at same amount of kilobytes? Anyone want to take a guess how much of the book now? It's 26%. Ooh, got a whole load of 44s. That's interesting. 26%. Not bad. Not bad. We can still do better. I'm not done yet. There you go. You people were talking about gzip. There's your gzip. Again, not going to dwell too much on the code. But this is it. There's a built-in set of libraries in .NET, take any binary stream and convert it into something an awful lot smaller. I think it works by I think it looks for patterns which recur throughout the binary and then just says, okay, those 4 patterns are all the same. They're all this, and there's 1 of them, there's 2 of them, there's 3 of them, and so on. I think that's the simple version. I'm sure there's a bit more interesting stuff going on, but that's the basic idea. Percentage of book now? It's 64% of the book. Again, bearing in mind, Pride and Prejudice, really big book. I think the audio book is about 20 hours long. It's pretty big. So this isn't bad. I could probably rest on my laurels just on that. Still 56K, but I can still do a bit better. So this is with 1 bit replaced, just the least significant bit. What would poor old Dan here look like if we started replacing more bits, as in the 2 least significant bits? Funnily enough, not all that different. I can now actually fit, just on this, I can now fit the entire book into the image, no trouble. It fits 129 kilobytes of data. That's a lot. and I've only replaced the two least significant bits, which means that you've got a variance pixel value by pixel value of between 0 and 3, which when you're looking at pixels, it's not very much. So that's a lot of data. 3 bits replaced. Still not very different. It's now 194K. 4 bits replaced. Wouldn't you know it? Now, if you look very carefully, we're starting to get a little bit of crackle here, and that's the result of the replacement of some of the pixel values. But even then, to be honest, I think I could pass this around, and someone would probably just assume it was an issue with JPEG compression or something. I don't think that would pass as anything particularly unusual. But that's 4 bits replaced. That's actually half of the binary of that has now gone. 5 bits replaced. Still not all that different. 6 bits replaced. Now we've crossed a line. We've obviously crossed a line here with 6 bits of replaced. So 6 bits replaced. There's only actually 2 bits doing any work whatsoever for rendering our image. And the weird thing is, I can still tell what it is. This line here is the line where Pride and Prejudice stops being written. All of this is actually just spare storage space inside my image. Someone says, rip the movie to MP4, upload the file at CDN, encode the URL into the file. Yeah, sure. To be honest, we're getting to the point where we could probably can encode a measurable percentage of the film into this thing. Well, maybe not. I mean, 389K, I don't even think we can get an MP3 into that. You could probably get all sorts of other things in, though. So that's 6 bits replaced. Let's see what happens if we keep going, because why not? 7 bits replaced. This is where the aliens went wrong in Independence Day. Absolutely. Plus, their spaceship is Mac compatible. Who does that? Now 389K. So finally, for the grand finale of this particular sequence of images, that's what happens if I replace literally all of it. That's completely useless, but doesn't it look cool? Just looks like flipping static. That's 389K's worth of data you can stuff there. That is not random. That is literally the text of Pride and Prejudice re-rendered as an image. It's utterly pointless, but I love it. So, nearly done, nearly done. One last idea to throw at you. Someone says they prefer that version, but then you can't see the desperate Dan. That's wrong. Poor old Dan. Okay, what if we wanted to hide our image, but we wanted to keep it completely image? What if we wanted to hide our text, but keep it completely secret? That is possible. You can actually hide it in such a way that it's completely impossible to dig out the original image unless you know a secret. So I'll choose a password. I'll use Jane, because why not? It's as good as anything. Jane also, of course, renders into ASCII and then on to binary. And what we do is you pair up each one of these values with one of the bits of Jane. So 0 to here. If it's a 0, you do nothing. You leave it as it was. If it's a 1, then you replace. So the second, so values 2, 3, and 4 were all 1s. So I'll go 2, 3, 4. That's these 3 guys here. They're all replacements. As it happens, one of them is a 0. Here it is. That's that 0, which was what it was before. So that's unchanged. That's a 1. That's a 0 gone from a 1. And then we've got 4 zeros. So ignore, 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 ignore. And then another ignore, and then a 1. So we'll change that from a 0 to a 1. The point is that I'm randomly scattering my binary data all through the file in an apparently random manner. And this is actually, as far as I'm aware, now unless a mathematician wants to turn around and tell me otherwise, but as far as I am aware, this is completely uncrackable in terms of security. Unless you know the secret, which in my case ain't very secret, but still, so long as you don't know the secret, there is no way to determine which bits are actual data and which bits are just whatever was in the image before. This technique is called chaffing and winnowing. which is fantastic term. Chaffing, this comes from harvesting, I believe, of wheat. Chaff is the bits of the wheat that you want to cut off and get rid of. So we are mixing our secret message in with the chaff, the original bytes of the data of the file. And winnowing is the process of separating chaff and wheat kernels. So winnowing is getting your message back out of it again. So what's the point of all this? Mostly none, in for honesty, but there's a couple of things you can do with it. First off, it's an awful lot of fun, and it is. I had a great time programming this stuff. If you want to have a mess about with some binary, if you want to do the computing equivalent of a magic trick, yeah, you could use it as a puzzle for those that are that way inclined that want an interesting puzzle. But also, this does happen out in the real world. This is being done. There are people who conceal secret messages in images and pass them around. Good people and some not so good people. They're all doing it. I have heard of cases where this goes on. So it is at least worth bearing in mind from a security perspective that this is a thing that can happen. If someone wants to smuggle a message, this is a fairly secret way of doing it. And I suppose, if you were so inclined, you could probably embed a text in a file. Maybe you could use it as a sort of copyright protection to show that you are the originator of this file because you were the one who knows the secret. You could do that. There's all sorts. So Kevin Smith says he was a kid. He used to hide images inside images. Yeah. I've seen some wonderful paintings from the 1700s where they do all sorts of clever things as well with that. Does anyone remember ADS? I do not. I have not. You could hide anything behind any file. I don't know what that is, I'm afraid. Look it up later on Wikipedia, kids. So does anyone have any questions at this point? Going once, going twice. Okay. Well, thank you very much indeed. You've been marvelous. I understand. Thank you. I understand though that means it's break. So thank you, Dave Mates Adventure there. Thank you. I understand that means it's break time now. So everyone go and get your beverage of choice and come back and listen to the next interesting speaker. Cheers, folks.